We're back for another recording, another lecture, presentation, whatever you want to call it, about blood vessels. So, where are we now? We are talking about capillaries. We got some capillaries right here. Got an arteriole hanging out over here, metarteriole here, venule over here. And these are capillaries. 1, 2, 3, 4, 5, 6, 7, whatever many you want to count here. And the thing is, check out these capillaries. There's no blood going through them right now. Because each of these capillaries, at its beginning, at its entrance, if you will, has a ring of smooth muscle. A ring of smooth muscle is a sphincter. Because these sphincters are before the capillaries, they're called precapillary sphincters. They're going to regulate whether blood is going into a capillary bed or just shooting through this thoroughfare channel here. So here's the thing. You got like 10 billion capillaries. You can't put blood in all of them all the time at once. So you got to have some capillaries closed. All right, and they're closed by these precapillary sphincters. Now, whether they're closed or they're open is determined by the activity of the tissue. The more active the tissue is, the more of these sphincters are going to open. Active tissues make heat, carbon dioxide, adenosine diphosphate, lactic acid, all things like that would open the sphincters. All right. Here we got Greg LeMond riding pretty fast in Paris. And as he's biking, as he's powering through the time trial here, what would the precapillary sphincters in his rectus femoris be doing? Well, his rectus femoris is his major quadricep muscle, which is going to be working here. So those guys would be relaxed and open. Meanwhile, in his large intestine, you'd expect those guys to be contracted and closed. Okay, let's move off capillaries for a sec and talk about veins. Veins are thin-walled, okay? They got all three of the normal tunics, but their walls are thin. Their walls are thin because they are low pressure. So they don't have to deal with high blood pressure like arteries did. So they don't need to have thick walls. Now, of the three layers, the largest is the TE, the tunica externa. That's kind of by default, just because veins aren't that muscular. Now, with thin walls, they do have big lumens. So their lumens, their spaces are big. And this is good. I mean, this goes hand in hand with the low pressure. Low pressure means it's going to be hard to push blood through. If it's hard to push blood through, we want to make sure the resistance is as low as possible. We achieve this by having big, fat lumens. One more thing about veins before we switch slides. Veins are also high compliant, which means they're stretchy. All right, you don't want them to get too stretchy though. And luckily, the media, there is some tunica media in here. The media has muscle. That muscle has tone, partial contraction, and that prevents overstretching or too much distension. Okay, because veins can stretch though, they often store blood. They serve as blood reservoirs. In fact, if you looked at where the blood is in your body, so maybe a fifth of your blood is in your pulmonary circulation, about a tenth in your heart. The other 70% is in your systemic circulation. And of that, look at the vein number here, 55 versus 5 for capillaries, 10 for arteries. So veins are reservoirs of blood. They're storing all this blood. What this means is that in a time of crisis, this reserve could be called upon. If you get up out of your chair, I'm assuming you're sitting down right now. Maybe you're walking and listening to this. Maybe you're driving and listening to this. I hope not. And let's say you're sitting down, you're at your house, all of a sudden you want to get up and run. If you get up and run, your skeletal muscles are going to squeeze your veins, pushing blood out of your veins back into your general circulation. Okay, let's keep going. Because veins are low pressure, there will be a tendency for blood to flow backwards. We prevent this by having valves. Here's a problem though. If the blood is pooling too much, the valve flaps, see these little valvey flaps in here? The valve flaps get stretched too far apart. You guys didn't just see the gesture I just made. I was demonstrating this with my hands. You can probably imagine it. And when that happens, when valve flaps get too far apart, when valves fail, we end up getting these things over here. varicose veins. All right, let's keep going. So actually, we're done with our anatomy. This is awesome. We now get to do some physiology. And one of our major physiological topics has to do with our capillaries. And it is about capillary exchange. So we know capillaries exchange things, oxygen, nutrients, hormones, CO2 wastes, water, etc., between blood and surrounding tissue fluid. Most of the stuff, most of the solutes, if you will, are exchanged by simple diffusion. Things go from areas of high cons to areas of low concentration. What we need to spend some time on, though, is the exchange of fluid, because it is weird. There are four major forces that affect the exchange of fluids between your capillaries and your tissue fluid. They include capillary colloid osmotic pressure, capillary hydrostatic pressure, interstitial osmotic pressure, interstitial hydrostatic pressure. So we got two forces in the capillaries, two forces in the tissues. Remember, osmotic pressure pulls water. Hydrostatic pressure is going to do the opposite. It's going to push water. All right, bear that in mind. Let's talk about capillary blood pressure. In other words, capillary hydrostatic pressure. There we go. What this means is that the blood pressure in the capillary physically pushes water out into the surrounding tissue spaces. All right. Capillary osmotic pressure. Mostly due to albumin, it is going to pull fluid from the tissue spaces into the blood. Interstitial hydrostatic pressure would be the pressure of the interstitial fluid. It usually is inconsequential because there is not a lot of interstitial hydrostatic pressure. There's no pump for interstitial fluid. There's no high pressure creator. So it's kind of inconsequential. If it did matter, it would push water from the tissue space into the blood. Okay. Interstitial osmotic pressure doesn't matter as well because there's not a lot of proteins in the tissue spaces. It would, though, pull water out of the blood into the interstitial space. Now, notice we claimed that two of them were inconsequential. So that really leaves us with capillary blood pressure and capillary osmotic pressure. And their balance determines overall whether fluid leaves due to hydrostatic pressure or comes back in due to osmotic pressure. And the balance of all these pressures is called the net filtration pressure. And you can do some math. I'm not going to make you do some math. But what you could do is, if you wanted to, you could do some math. You could figure out in a capillary, you could start on the arterial end. You could figure out, well, how much force is pushing water out? How much force is pulling water in? And you realize at the arterial end, blood hydrostatic pressure is greater than osmotic pressure. There is net pressure out, so you'll lose fluid on the arterial end. Notice we have three arrows indicating fluid loss. However, on the venous end, you can do the math too. And you don't have to do the math. You don't have to know the numbers, but you got to realize what's going on here. The venous end, osmotic pressure is greater than blood hydrostatic pressure, so fluid comes in. But notice we only have two arrows here. The pushing out at the arterial end outweighs the pulling in. This is good because it makes us tissue fluid. We got to have tissue fluid. So you always end up losing a little more than you pull back in. All right. If you look at a graph here, you can see capillary blood pressure in the beginning outweighs osmotic pressure, but at the end, capillary osmotic pressure outweighs capillary blood pressure. Notice this drops as you go farther and farther from the heart. COP remains the same because albumin levels remain the same. And this part is going to outweigh this part. So you end up losing more fluid. You end up doing more filtration than you do reabsorption. You don't pull in as much fluid. And we said this was good because we make tissue fluid. So you end up doing more filtration, fluid loss, than you do absorption. So you're making tissue fluid. But you can't just keep making tissue fluid over and over again. Somehow, that tissue fluid has to have a way to get back into the blood. And that is done by a system of lymphatic vessels. And by the way, if that doesn't work, this is what happens. Too much tissue fluid. In other words, edema.